Hello students, so this is our first class on Introduction to FEM. So FEM is the most widely used numerical tool for analysis of continuum problems in engineering, science and mathematics. So it is a numerical tool, that means you cannot expect to get a closed form solution from it, and it analyzes continuum which is represented by a partial differential equation or a set of partial differential equations, and finite element actually discretizes the space. That means it divides the whole space in small elements. So finite element is applied in structural and solid mechanics, in heat transfer, fluid flow, diffusion, electromagnetics, etc. So in mechanical engineering, we extensively use finite element in engineering design, and the process is something like this. So in design, we first make a guess design, and then we analyze the guess design, and if all the outputs are satisfactory, that is the design objectives are met, then we accept the design. But if the design objectives are not satisfied, then we modify the design and we again make an analysis of the modified design. So this is an iterative process, as you know, and role of finite element is here in the analysis. So we use finite element method for analysis. So here in this course we'll follow follow this book as text. That is first course in FEM by Daryl Logan, and these two books will be considered as references. So the first one is Concepts and Applications of FEM by Cook, Malkus, Fleisch and Witt, and the second one is Finite Element Procedures by K.J. Bale. But these two books are a little difficult for you, for the beginners. So first let us start. We can start with this book. This book is simple, and once we learn the basics, we can start reading these books. So first we deal with the simplest element, and that is the spring element. So a spring element is the simplest element, and we'll find out the stiffness matrix of this spring element. As you know, this spring has got a stiffness K, but what is the stiffness matrix of the spring, that we'll find out, and later on we'll see all the elements in finite elements, they have got a stiffness matrix. So we also will try to understand what is the meaning of this stiffness matrix. So these two ends of the spring are called the nodes of the spring. So this is node 1 and this is node 2. So node 1 can move in this direction, so it has a single degree of freedom u1, and the node 2 has got a single degree of freedom u2. So we consider 2 degrees of freedom for this element, that is this node, the movement of this node in the axial direction, and the movement of this node in this axial direction. So this is a 2 degrees of freedom problem, and since this is a 2 degrees of freedom problem, the stiffness matrix will be 2 into 2 in size. So now how we can find out this K11, K12, K21, K22, or rather this Kij's from first principle. So the definition of Kij is force at DOF I force at DOF I and force on the element. You have to remember, force at DOF I on the element due to unit displacement at DOF J, keeping all other DOFs fixed and other than J, keeping all other DOFs other than J fixed. That means if we want to find out K11, so we have to find out the force at DOF1 on the spring, and the force will be on the spring due to unit displacement at DOF1 because J is also 1 here, keeping DOF2 fixed because it is other than 1. It will be other than 1. So keeping DOF2 fixed. So since DOF2 is fixed, we fix this DOF and we apply U1 equal to 1. And we find out that due to this U1 equal to 1, what force should be applied on the spring? So, and you know, the force applied on the spring is F1 equal to K. That means that is K11. So K11 is nothing but K. Now what about K12? K12 is force at DOF1 due to unit displacement at DOF2, keeping DOF1 fixed. Keeping DOF1 fixed. So we fix DOF1 here. We fix DOF1 here, and we give an unit displacement at DOF2, that is U2 equal to 1, and we find out what is the force on the spring at DOF1. So if you give a force here, if you give a displacement 1 here, then the force on the spring will be this one. So that is minus K because the force is in the negative of x direction. So it is minus K. So K12 will be minus K. In this way, you can find out K21, that is force at DOF2 due to unit displacement at DOF1, keeping DOF2 fixed. So if you give a unit displacement here, the force will be in this direction. So F2 is again minus K and K21 is minus K. And K22 will be force at DOF2 due to unit displacement at DOF2. So if you give a unit displacement here, then the force here on the spring will be again equal to K, but this is positive. So K22 will be equal to K. So the stiffness matrix is K minus K minus K, K. So this is the stiffness matrix, means this F1 and F2 is this K into U1 and U2. That means F1 is, here F1 is K11 U1 or K into U1 minus K into U2, and F2 is minus K into U1, and F2 is minus K into U1 plus K into U2. So this is the stiffness matrix which relates the force at the 2 degrees of freedom to the displacement at the 2 degrees of freedom. So this is called the element stiffness matrix, and this is the element stiffness matrix of the spring. Now what are the observations here? The observations here are the stiffness matrix is symmetric. So the non-diagonal terms are equal. And the stiffness matrix is singular. That means if you find out the determinant of the stiffness matrix, you will get 0. And the stiffness matrix is positive semi-definite. So positive semi-definite means you take a non-trivial. Non-trivial means where U1 and U2 both are not zeros. And any vector U1, you take any vector and you perform this operation. So let U be U1 U2. That means U transpose KE U. So if that is greater than 0, then we call it positive definite. If that is less than 0, we call it negative definite. And if it is greater than equal to 0, then we call it positive semi-definite. And from here you can see, if you multiply, then see this is this. If you multiply this with this, you get this, and this term is this. Then if you multiply again, so you get this. So ultimately you get k into u1 minus u2 whole square. So a whole square cannot be negative, so it has to be greater than equal to 0. So this u transpose ku has to be positive semi-definite. U transpose ku to be positive semi-definite. So in this class, so we'll be frequently using Octave. So this is the first screen of Octave, and you know Octave is a open source software by John W. Eaton and others. So which is having the almost 99% same syntax as MATLAB. I do not know whether it is exactly 99 or not, but it's almost same as MATLAB, and it is open source, so you can easily download it. But it has very less number of modules compared to MATLAB. But you can always do the basic computations in Octave, and you can write codes in Octave just like you can do it in MATLAB. So I would definitely suggest you all to use this Octave, and here also we'll be using Octave. So see how simple it is. Suppose we want to make this k as a matrix. So we want to assign a matrix to this variable k. So suppose we write it like this. Suppose okay, let us call it stiff. So stiff is a matrix, the stiffness matrix, and the stiffness matrix is, say, 1000 minus 1000 semicolon minus 1000 and closing of third bracket, and you enter. So this is the matrix stiff, and you find out the determinant of that matrix by simply using the det command. So determinant stiff is equal to 0. So that shows that your stiffness matrix is having a 0 determinant and it is singular. And again you can find out the rank of the matrix. So the rank of stiff means answer is 1. So it has not got a rank of 2, it has got a rank of 1. And suppose you just define a vector u equal to, say, 2 2, or rather a column vector. So if you give semicolon here, then it will go to the next row, and if you give a space here, it will go to the column. That means u equal to 2 2 will be like this. If you put a semicolon here, so it will be a column matrix, and without this it will be a row matrix. Then if you do u transpose is nothing but the single quote into k, or not k, is stiff. We have defined stiff into u. So that is 0. So when you are taking the two elements of u to be equal, you are getting 0. Now if you just use this up arrow key, so if you take u equal to 2 3, then and again if you repeat stiff u, just use upper arrow to get the previous commands, then you get 1000. So see, it is a positive semi-definite matrix, because you can get 0 or you can get a positive number. Never can you get a negative number. Anyway, let's continue. So now we see how we can assemble two spring elements. So this is element number 1, this is element number 2, and these are now the 3 degrees of freedom. So this U1 and U2 are degrees of freedom of element 1, and U2 and U3 are degrees of freedom of element 2. And this stiffness, this spring, the first spring we assume to be having a stiffness of K1, and the second spring has a stiffness of K2. So the stiffness matrix for this is K1 minus K1 minus K1 K2, and the stiffness matrix for this is K2 minus K2 minus K2 K2. And you see here, since there are 3 degrees of freedom, for this whole system we'll get the stiffness matrix as a 3 by 3 matrix. So these elements are having a 2 by 2, both of these elements, each of them are having a 2 by 2 stiffness matrix. These are element stiffness matrix, but the whole system will be having a 3 by 3 system matrix, 3 by 3 system stiffness matrix. So now see here, just note the blue one and the orange one. So that means the 1 degree of freedom U1, the 1 degree of freedom, the 1 degree of freedom here, the 1 degree of freedom here has gone to 1 degree of freedom here. The 2 degree of freedom here, the degree of freedom 2 here has gone to degree of freedom 2 here. So similarly for columns 1, 2, whatever will be there for rows, the same thing will be there for columns. And for element K2, its 1 has gone to 2 and its 2 has gone to 3. So the blue ones are called the local degrees of freedom, and these red ones are and the orange ones are called the system degrees of freedom. So similarly 2, 3, 2, 3. That means, so now this is the equilibrium equation for element 1, and this is the equilibrium equation for element 2. Now this is the system stiffness matrix. In the system stiffness matrix, let us call it 1, 2, 3 and 1, 2, 3. Let us number it like this. So in this space 1, 1, what is here? This 1, 1, this, just notice the orange numbers. So 1, 1, this K1 will come here, and row 1 column 2 minus K1 will come here. See, from this element, that is element number 2, you do not get any contribution either in place 1, 1 or in place 1, 2. So 2, 1 will come from here, so minus K1. But in 2, 2, we have contributions from, this will be 1, sorry, this will be 1. In 2, 2, there will be contribution from here, and there will be contribution from here. So in 2, 2, we'll put K1 plus K2. And in 2, 3, there will be contribution only from here. There will be contribution only from here. So we put minus K2 in 2, 3. In 3, 1, there is no contribution from either of the elements. 3, 1 means 3 row 1 column. See, 3 row 1 column is not here, it is also not here. But 3, 2 is here. 3, 2 is not from here but from here, and 3, 2 is minus K2. So 3, 2 we put minus K2, and 3, 3 is also from here, so we put K2. So this is your system stiffness matrix. This is your system stiffness matrix, and U1, U2, U3 is, and here similarly, just simply in first row F1, 1 is there. So we are talking about the assembly of the forces. So corresponding to the first degree of freedom, the forces F1 on element 1. So here the first degree of freedom F1 on element 1. The second degree of freedom is here. Second degree of freedom is F2 on element 1. So here in the second degree of freedom we are getting F2 on element 1. But from here also the second degree of freedom is coming, which is F1 of element 2. So this F1 plus element 2 will be added to this. And for the third degree of freedom, F2 of element 2. So the right hand side is this. So here you see we have rather mechanically assembled the stiffness matrix of stiffness matrices of two elements, and we got the system stiffness matrix. And this process can also be implemented in a computer program, as we will see later on. But the next thing what we want to see is that the stiffness matrix which we have got here, or the force vector which we have got here in the right hand side, are they correct? So if we apply equilibrium equations, then do we get the same thing? So this is an explanation is here. So this is the first spring. So for the first spring, let us assume that U1 of 1 is greater than U2 of 1. That means the spring is in compression. That means this force on the spring is in the positive direction. So this F11 will be K into U1 of 1 minus U2 of 1. So this is the first equation. Now suppose U2 is greater than U1, then obviously the spring is in tension. So F2 of 1 will be in this direction, and that is K1 multiplied by U2 minus U1. So this is the second equation. And similarly for the second element, F1 on element 2 is K2 into U1 minus U2 when U is greater than U2, and it is U2 minus U1 when U2 is greater than U1, that means the spring is under tension. So these four equations are okay. So we name them 1, 2a, 2b and 3. Now let us keep 1 and 3 as it is, and we add 2a and 2b. So, and in that we use the system numbering. So U1 of 1 is U1 in the system, U2 of 1 is U2 in the system, U1 of second element is U2 of the system, and U2 of the second element is U3 of the system. So this encircled suffix, this encircled number is actually the element number, not suffix. This encircled number is the element number. So U2 of 2 is U3. So now if you write this equation, then it will be K1 U1 minus K1 U2 equal to F11, and here K minus K1 U1 plus K1 U2, because U2 of 1 is U2, and U1 of 2 is also U2. So this and this will get added up. So K1 plus K2 into U2 minus K2 into this is U3, minus K2 into U3 is equal to sum of these two terms on the right hand side. So this is this, and the third equation is minus K2 into U2, because U1 of 2 is U2 plus K2 of U2 of 2 is U3. So this is the third equation. So in matrix notation, this is this. So this is same as what we got here. So we are not violating the equilibrium equations, that much we are sure. Now what about the right hand side? So what is F11? F11 is actually this one. This one means the reaction coming on the system from its supports. Similarly, F2 of 2 is also the reaction. So F1 of 1 and F2 of 2, F2 of 2, that means here they are nothing but the reactions coming on the system. And what about this term F2 of 1 and F1 of 2? Suppose this is the system and this is the first spring and this is the second spring, and we separate out this node like the method of nodes, or method of joints, and we show a force opposite to this here and a force opposite to this here. So since there is no external force here, so the summation of these two forces has to be 0. So this is nothing but 0 when it is case 1, that is no external force on DOF2. But when there is an external force, so this is something we get as a free body diagram of the node 2, and here this is the equilibrium equation and this is the equation. So this has to be replaced by P, and that is what is exactly done here. So for here, when there is no external force, we put a value of 0 here, and when there is an external force, we put the value of the external force here. And here we have shown 3 elements, they are connected. Here F1 of 1, that is force at the first degree of freedom of element 1, and the force at the second degree of freedom of element 3. They are actually the reaction force coming on the system. And here, since at the degree of freedom 2 there is no external force, so we put 0 here, and here you have an external force of P, we put P here. The numerical example will be considered in the next video. Now let us work out one numerical example which will clarify our ideas. So this is a 3-element system where the first node is fixed and the last node is also fixed. So there are 4 degrees of freedom: U1, U2, U3, U4. So the stiffness and you know the value of K1, K2, K3 are given, and P and Q are also given. And you know that finite element always works with numerical values. It can never work with symbols. Or it does not work with symbols. So this is the stiffness matrix. Since the stiffness K1 is 1000, this is the stiffness matrix for element 1. K2 is 2000. So this is the system. This is the element stiffness matrix for element 2, and this is the element stiffness matrix of element 3. This one. Now, when we assemble, this 1 1 goes here, 1 2 goes here, 2 1 goes here, 2 2 goes here. So the system has 4 degrees of freedom. So the system stiffness matrix will have 4 by system stiffness matrix will be 4 by 4 in size. And 2 1 will go here, 2 2 will go here, but 2 2 will also come from here. 2 3 will come from here, 3 2 will come from here to here, and 3 3 will be here, but at 3 3 this will also come. 3 4 this will be here, 4 3 this one, this 4 3, this 4 4 4 4. I think it's here. This is the assembly of stiffness, and if you assemble the forces, so F1 1, that is force at DOF1 of element 1, force acting on the system and not the force acting on the support. This is the force acting on the system on DOF1 of element 1, and here the force acting on the system on DOF4 of element 3. So, or DOF2 of element 3, which is the DOF system DOF4. So these two are coming from the reactions, and these are support reactions actually, and working on the and are applied on the system, and these are the external forces. So 10 and 20. So this is the right hand matrix. So this is the equation. But if you want to, if you just carefully notice that u1 is 0 and u4 is 0, so u1 is known and u4 is known, but F11 is the reaction force which is to be determined. F2 of 3, that is also the reaction force which had to be determined. On the other hand, these 10 and 20, the external forces, these are known, but these displacements are not known. So if you want to solve the matrix, since you just like simultaneous equations which you solve, the right hand side is not fully known. So what you have to do is, you have to take this equation and this equation. So for the first equation, you get minus 1000 into u1 plus 3000 into u2 minus 2000 into u3. So this is 0, so u4 will not come into picture, is equal to 10. And from this, minus 2000 into u2 plus 5000 into u3 minus 3000 into u4 equal to 20. Or u1 is known, so you can take it in the right hand side. u4 is known, so you can take it in the right hand side. So there is a problem in sign, I suppose. So let us put, so this is plus, so this should also be plus. It should be plus. So let's put this, it should be plus. Okay, and here 10 plus 1000 plus or minus 2000 u2 minus, oh this is minus, so here this should also be minus. So that is a problem in sign, so this should also be minus, should also be minus. So when it goes to the right hand side, it becomes plus. Okay, so this is the thing, but since u1 and u4 are 0, it doesn't matter much, so we are left with this equation, and we have to solve this equation. So when we solve this equation, we get u2 is this and u3 is this. So we can easily solve this equation. You can, so 3000 minus, okay. So let us say stiff equal to 3000 minus 2000. So 3000 minus 2000. Then second column, second row rather, minus 2000. It has to be symmetric, and 5000. Okay. So this is the stiffness matrix stiff, and the right hand side, the F we call, F is 10 and 20. So further remember. Now let us continue. So U is 10 20, not 10 20, it is 10 semicolon 20, enter, so 10 20. So this is stiffness matrix and this is the right hand side, and if you just do this, this means stiff inverse F. This slash, what is this called? This slash is means stiff inverse F, and if you enter, these are the solutions. So here, so here these are the solutions. Now these are the 4 displacements at the 4 degrees of freedom. Now if we, this is our system stiffness matrix. Now we know the full U vector. So these are the values, and if you multiply, then you get this as F1 of 1 and this is F2 of 3. So these are the reaction forces acting on the system from the supports, and these are automatically coming as the external forces. So this is a check that you have got your displacements correct. Otherwise these two would have matched. So F1 1 and F2 3 are the reaction forces, and also you can see that the total external force must be equal to the total reaction force and the direction should be opposite. So 10 plus 20 is 30, and if you add this and this, you get also minus 30. Now element wise you can get the forces. Suppose element 1, so this is the element stiffness matrix, and what are the 2 degrees of freedom of this element? This U1 and U2 are the 2 degrees of freedom. So displacement corresponding to these 2 degrees of freedom, and if you multiply, then you get this. So this element, for this element, the force is in the other direction and this force is this. So this element is under tension. And for element 2 you take U2 and U3. So for element 2 you take U2, for element 2 you take U2 and U3, and you get this. So this is this, and this is actually in the other direction because this minus is there, so it is in compression. And for element 3 you take U3 and U4. So U3 and U4, if you multiply, you get this and this. So this element, sorry, here I have made a mistake. I should have shown it. All DOF should be shown in their positive direction. So this should be this. Okay. So this should be. So this element is under again compression. So now if you again, now this is the first element, this is the condition of the first element, that is the condition of the second element, and this is the condition of the third element. Now you put them together. What do you get? This will come here, this will come here, and here these two will get added up and give you 10, and here these two will get added up and give you 20, and here minus 20.8. So this is the picture of the total equilibrium where you get back the applied forces. So this is again a check. Now you may ask that this spring element, so what I want to tell you, not you will ask, that this spring element is same as this bar element, because when the bar is in tension, its stiffness is AE by L. So though we have shown springs here all over this first lecture, so you can also use the same thing for bars. So students, we finish our first lecture here and hope you understand. So since this is a new mode of teaching, I always insist that you give your feedbacks so that this can be improved. So thank you very much.